let's first recall what we have been talking about in the last lecture. We have been talking about the basic MDP formulation. Just very briefly recall, when we talk about MDP, we talk about MDP has the following elements. The first, we have a set of states, and we also have a set of actions, and we have a reward function and a transition probability, transition matrix. And finally, since we're always talking about the episodic setting in this class, so we will have a finite horizon H. Okay, this is the first thing we're talking about. And then the next, we talk about what we call environments and policies and values. So we know the environments, we typically just means the elements P and R. And we will first talk about the case of known environments today. And later we will talk about the learning scenario where we're actually exploring in the unknown environments. So we actually need to learn those P and R from some data, from observations. And then we also talk about the policy. So policy is the first tricky part. So we first talk about there are two kinds of policy. One is we will spend a lot of time on, that is called Markov policy. Okay. Markov policy can be viewed as I have a policy pi that is equal to a bunch of functions. We actually have H functions. And each function is a map from states to either the action set or the probability simplex of action set. It depends on whether it's deterministic policy or it's a stochastic policy. So we also have a general policy. We say in general, we don't necessarily need to pick this special form of policy. So the general policy is, again, we have this pi is equal to, we need to specify this policy. We just need to specify the policy at each step. The only difference is now this policy can be a map from all the possible histories. That is S times A to the power of H minus 1 times S. These are all possible histories, again, to the set of action or set of distribution of action. Okay, so in general, like you can think this general policy is basically history-dependent policy. Well, this Markov policy is, you can think it's more like history independent. It only depends on the current states, but does not depend on the history before the current states. And finally, we talk about the value in the last lecture. So we'll just quickly talk about the VH. Okay. So this is the value of, I would just first say this is like you should think this is a value of Markov policy. We'll talk about the reason later. So the value is defined as expected cumulative rewards after step H. So it's a summation of the rewards from each step to the final step. Condition on the current state S is equal to S. Okay. We also talk about the Q value, which is a function of SA, which is essentially the same thing. But a condition on the current step, the state is S and the action is A. Okay. So one thing I want to emphasize a little bit is this value. Okay, so because we have like two different policies, we have Markov policy and the general policy. Clearly, this VH is defined for Markov policy. This definition is well defined. For all H and S, for all states and steps. Okay, this has no problem. But the only thing I want to be careful is when we written this kind of definition, and when we talk about later steps or later states, we actually realize like for general policy, it's not very well defined. I think the reason is this kind of like already assumes whatever the cumulative rewards in the future only depends on the current state S. Okay, it doesn't depend on the history. Well, on the other hand, the general policy depends on history. So for general policy, you cannot necessarily write a value only depend on current state, but also need to depend on entire history. Okay, so in general, like this VH should depend on the entire history. Okay, I will use just tau h to specify the S1, A1, S2, A2, till SH. Okay, so we can no longer just use this definition. However, we notice at the very first step, V1 is still defined the same. Okay, because in the very first step, we don't have like any further history. So in the V1 case, in the first step, we can still use exactly this definition. Okay. So finally, I think in the very last part of the last lecture, we talk about objective of IL. We want to define the optimal policy pi. Pi star, which maximize the value at the initial state, which is essentially at the beginning state of the game. Okay. And let's just, for simplicity, consider, without loss of generality, consider we have the fixed initial states case. We already said we can, if you are not happy with fixed initial states, you can think initial states is sampled from some distribution. But all the proof, all the analysis we're going to talk about today easily extend to that kind of scenario. So for simplicity, we just say we have a fixed initial states. Okay. And for chess, essentially, we always start with the same configuration, which is initial states. And this is essentially kind of says if you are playing some policy pi and what is your win rate by using that kind of policy. Okay. Okay, so we stop here in the last lecture. So today we will continue talking about how we're gonna compute the value and also what's the relation, how we compute the value and how we compute the optimal policy. I think the first thing I want to do is since we can raise this general policy issue, it seems like a very complicated. If we always need to talk about Markov policy and general policy, and in the last lecture I already said that in the MDP scenario, in a single agent, like this Markov decision process, we can, without loss of generality, talking about Markov policy only. So we don't need to go to the complexity of talking about this general policy. So what is this reason? So this is the first proposition we're going to talk about today. Proposition 1, we're going to say for any general policy, pi, there exists a Markov policy mu. So that the value of the entire game, that is starting at the first step with initial states, is equal. Okay. I just want to sanity check that Markov policy can define this, and for general policy, the later step is more complicated, depends on entire history, but even the first step, you can still define it in terms of the initial states. So both quantities are well defined. And this is essentially says, if my final goal is I just want to maximize my winning probability or something, I want to achieve the highest value, without loss of generality, we can talk about the Markov policy, because for whatever the value can be achieved by general policy, I can essentially construct some other Markov policy that may depend on this general policy and achieve the same value. Okay? So this immediately implies that there exists at least a non-optimal policy. That is Markov. Okay, any question about the logic here? If not a question, I think we will first just spend some time prove this proposition 1. Since this is like a mathematical foundation, I think a lot of mathematical courses are like constructed in this way. We first talk about the proposition, which proposition or theorem or lemma, which are the important thing, like carry the meaning of like a high-level idea of what is going on. And then we talk about the mathematical proofs, like to support this kind of claim. Okay. So the proof of this proposition is relatively easy if you're very familiar with like this kind of notation and probability. So we'll just do the proof for now, and a lot of proof in the reinforcement learning is by like induction, because it's like we need to prove like first step is correct and second step is correct and those kind of things. Okay, so we will just do it here. So let's first write out what is the value of this complicated like a general policy pi. So we start with some general policy. We want to essentially, we say there exists a Markov policy. We will prove by construction. So we'll construct some Markov policy that depends on this general policy so that we can achieve the same value. Okay. So let's first write out a definition of this value. We already kind of like say it here. It's summation of h equal to 1 to capital H. Okay. We kind of like put the summation outside. And inside we have the expectation over pi. And the reward h step, sh, ah, conditional on the first state is s1. Okay. This is just basic definition. Only thing we did is like exchange the expectation and the summation, which we already know is we can do it. Okay. So the second thing is we explicitly write out what is this expectation. So expectation, essentially, we just summation over. So here, the only randomness in this reward is just this sh and ah. Those are the random variables. So the expectation essentially is just summation over all the possible values of those random variable and times the probability of those random variable. So we summation over all the possible values of sh, ah. And we say we use the probability pi h of sh, ah, conditional s1. This is the probability of reaching sh, ah, follow the policy pi at step h, and times the reward of sh, ah. Okay, just want to say this is the probability visit sh, ah at step h. If starting from S1 and follow pi 1. Follow policy pi. Okay. So, and also things we always just consider, we kind of start from the fixed initial states, S1. So for simplicity, to simplify the notation, we will use this pH, pi, sh, ah, to directly just means it's conditional on S1. Okay, because this is like fixed initial states. This is fixed. So when it's clear from the context, let's just always say, if we don't, even if we don't anything, we actually just mean we condition, we fix this initial states. Okay, so let's just simplify this notation. So what do we learn from this equation? This essentially says the value is just equal to the reward of each possible state action pair times the probability of possibly visit those kind of state action pair, and then with summation of all of them together. And this not only holds for pi, also holds for mu. Essentially, this holds for any policy. Okay, not only just the particular general policy pi, but also holds for whatever the Markov policy we're going to construct for mu. So this implies, if finally we just want to prove v1 pi s1 is equal to v1 mu s1, there's another way we can prove this statement, which essentially we just need to prove the probability of reaching any state action pair at each step if follow policy pi is the same as the probability of reaching any state action pair at step h follow policy mu for any SAH. Okay. Because we can see on the right-hand side, there's only one thing that depends on the policy, that is this probability. Everything else is independent of policy. So that's why as long as we can prove the visitation, this is also called the visitation measure. As long as this visitation measure is the same for different policy, then the value is the same. Okay. So the way we're going to construct this Markov policy to match the value is basically by this criterion. We will construct a Markov policy so that we will match the visitation measure. Okay. We will match the probability of visiting any possible state action pair. Okay. So in order to prove this, let's first, we'll do this proof by construction. So the idea is we're going to construct some policy mu so that this is true. Just remember, in order to construct some Markov policy, all we need to do is we constructed a Markov policy at each step. Okay? So we essentially need to specify what is the value of this Markov policy, mu h, at each step. That is the probability of taking action A conditional on current state S. Okay, let's say in general, this is like stochastic policy. Okay, so this is what we want to construct. And what we have here is we have some Markov general policy, that pi h, which kind of like depends on the action A and also the entire history tau h, where the tau h is equal to S1, A1, till SH. Okay, so this depends on the entire history. So a simple idea of connecting those two policies, like we want to match this probability, is how about we just do some averaging thing. Because on the left-hand side, we only depend on current state and current action, where on the right-hand side, we depend on the entire history. So one thing we can get rid of this history is we're just taking expectation over those histories. Okay? So this is essentially the idea we're going to do. So we're going to say we will construct this policy, which is equal to taking average over the general policy, and the condition on this sh equal to s. Okay. That is, the right-hand side originally depends on a, s1, a1, s2, a2 till sh. And then we're gonna just fix the last state to equal to s, a is equal to a, and I'm gonna take an expectation over everything. So this is essentially some straightforward idea we can think of. And then all left is we need to test whether our construction actually delivers something like this, actually deliver this property like this. Okay? So first thing is we need to, since this is a conditional expectation, we need to write the mathematical definition, or like how we're gonna compute this conditional expectation. So we know the conditional expectation is just equal to the probability of this joint probability over the probability of this whatever we condition on. Okay. So we can write this equation, which is equal to, on the denominator, that is the probability if following the pi to reach s in each step. Okay, so this is a probability of what we condition on. And then on the top, on the numerator, is the joint probability, which we can write it out, that is equal to summation of all tau h, so that sh equal to s. And then the probability of visiting tau h times the pi h of a given tau h. Okay, so this is essentially the definition of this conditional expectation, or we just compute it out. And the only thing it relies on is we require the denominator to be non-zero. Otherwise, this is like L-defined. Okay. So that means we need to fix something. If this is equal to 0, so what are we going to do? So it turns out that when this is equal to 0, it doesn't matter, because when we follow the policy pi, we will never visit that kind of state. So it doesn't really matter what kind of policy you play on that state. So you can just be arbitrary policy. For the states that the probability is equal to 0. Okay, so this gives a more rigorous way of defining what is this Markov policy to be, and all the remaining thing is we just need to check they generate the same visitation measure. Any questions so far? Okay, so now it remains we will use induction to prove this star claim. That is, by our construction of mu, the mu and pi will generate the same visitation measure over all state, action, and step. And the approach we're going to do induction is essentially we're going to argue in the very first step this is true, and then the second step this is true, and then third step is true. So we're going to do induction over H. Specifically, we're going to do the following. That is, we will first argue that pH mu s is equal to pH pi s. If this is true, then this is going to imply pH mu SA. That is, the probability of visiting SA at each step is also equal to pH pi if following policy pi if visiting SA. And then we're going to use this to imply that pH plus 1 mu s is equal to pH pi s. So we're going to prove first step and the second step. So this is how we're going to do induction. That is, for any h, I'm going to prove that this claim will imply this claim. And the second step is prove this claim will also imply this claim. And then we can do induction from the first step, okay, because we can check the very basic case. So the base case, essentially, we just need to check at the very first step. Because first step, we're doing the fixed initial states. So actually, the probability of visiting S1 is kind of like irrelevant to the policy. So we immediately know this is true. Okay. This is true, things S1 is fixed. Okay. So all remains is just we prove 1 and 2, like why 1 and 2 are true. And 1 and 2 are essentially followed by some calculation of basic probability. So we'll first say the pH mu. We'll prove 1 first. So essentially, we want to first look at this pH mu SA. This is what we want to prove. This is equal to this. And this we know because it's Markov policy. It's equal to probability of visiting state S at each step, and times the probability of taking some action A given condition, given S. This is essentially the probability. This is essentially the stochastic policy where the probability of taking some action A condition S. And finally, we know this is equal to P pi of S and mu h A given S. This is by induction hypothesis. So on the other hand, we can also start from the other side we want to prove, which is the probability of reaching some state action SA pair at step H follow the general policy pi. And this we need to be slightly careful. And this we can no longer do this decomposition. Essentially, we need to summation over all the possible history so that the final step is equal to S. And we see the probability of H of if following policy pi to visit those history and action pair. Okay. By doing this decomposition is because now we can do the similar decomposition that we can decouple the A from this trajectory pi because now the general policy actually depends on the entire history. So this is equal to summation over tau h sh equal to S. And we say this is equal to the probability of following policy pi to visit some trajectory tau h times the general probability of taking some action A condition on tau h. Okay. So this is essentially also everything we can do on this side. So we can see if we want these two to be equal, then we have to make some policy pi to satisfy some special condition. Fortunately, we already say our construction of pi is equal to this formula. And we can directly plug this in. And we realize when we do this kind of cancel out with the denominator. And whatever on the numerator is exactly equal to this. So this is essentially, those two are equal by definition, by construction of mu. Okay. That is, our construction seems like to have some reason, and which precise reason is to make these two equal to each other, so that our first step essentially holds. I think this is a bit more about mathematical calculation, but the whole intuition is like we just want to have some construct some Markov policy, which is averaging, so that we're more or less guaranteed this is true. Okay. Now the first step is true. All we need to do is the second step. P mu sh plus 1 sh plus. This we also start from the probability of visiting some s in the next step, h plus 1 step. Okay, let's just say this is s plus 1, so that to make it clear. And we know this is obviously equal to summation over all SH, the probability of visiting all the tuple of SH, SH plus 1. And in general, we can say this is equal to SH, the probability of mu that essentially we decouple this thing, that is equal to the probability of visiting SH plus 1 condition on SH, times the probability of visiting SH. Nothing very fancy. I think the most important part is now we realize this thing. This thing essentially is the transition in MDP. So essentially we already say the transition structure actually incorporates some Markov structure in it. So that the key thing to observe is this thing only depends on the transition P, but it does not depend on mu. Okay. So essentially, we can get rid of this mu dependence here. And this is essentially the key step where we kind of use this Markov property so that we can say we don't need the general policy. So the remaining steps become relatively straightforward, that we say this is equal to, so first we want to use the induction hypothesis, where induction hypothesis says P mu on SA is equal to P pi on SA. So we can replace this mu by pi. So this is equal to summation SH, PH of SH plus 1 given the current state in SH, action in H, and times we just replace this by pi. Okay, this is by induction hypothesis. And finally, we can also do the same argument that this thing doesn't depend on pi. So it doesn't matter we put pi here or not, they are the same thing. So we can also just add a pi here, and then this becomes pH pi of sh plus 1, which is exactly just equal to, pH plus 1, let's just say pH. H plus 1, pi, and sh plus 1. Okay, and this finished the entire proof. So after you get you get used to like this notation of MDP and how the probability gonna generate each other, and those proofs are gonna be a piece of cake. And only important idea is how we're gonna construct the Markov policy that's gonna essentially match the same value of general policy. Is just by averaging over all the history. Okay. Any question about this part so far? Yes.
I'm just making sure that second part of the proof is just saying like, oh, if they both have the same probability of getting to state S and action A is of H, then they both have the same probability of getting to state S H.
H plus 1, yes, exactly, yeah. That's cool. Okay, so don't worry if you kind of like feel some steps missing here. And I guess the important part is about the claim. Like we realize now that we don't need to look at the general policy at all if we only care about MDP, and we can, without loss of generality, only talk about Markov policy. So from now on, in the odd MDP part, we will just focus on the Markov policy. So whenever we talk about policy, we actually mean Markov policy. Okay. So before we move forward, I want to talk a little bit about some notation that's probably going to be used in this lecture. So for now, I think we just consider everything as a tabular setting. So we consider like we have some finite states and a finite action. Like the state set, cardinality is equal to S, and the cardinality of action set is equal to A. Let's for now say something like that. And then we use this value of some state at each step. This is like some single value. Is some single scalar, real value single scalar. And sometimes we will use some notation like this V pi h without indicating what is S. You can think this is a function, but you can also think this is a vector. So this is a vector is in like the S-dimensional vector. You can essentially, this is a vector so that the first dimension is like the value on the first state. Second dimension is, second coordinate is the value on the second state. Okay. So similarly, you can also consider the Q value as a vector of SA dimension. Because essentially each state action pair corresponds to one coordinate of this vector. And finally, we will also use some succinct notation in reinforcement learning because we're going to use this a lot of time. So a lot of times we're gonna face some expectation of the value of the next step. S prime condition on SA. Okay, let's say this is at H step. And this thing we know by definition is equal to taking expectation that S prime is generating from the probability of like a transition probability condition on current state action, and it goes to the next states, and then Vs prime. So the complicated part about this notation is like we have this dummy variable S prime and S prime. Like we need to write it twice, and which makes this notation a bit more complicated. So for a lot of times, we will just write a succinct notation. We will just use this PHV, and depends on SA. Sorry, let's just do it here. Okay. So we define this notation to essentially suppress the dependence on S prime. So it really is just taking expectation of the value at the next step, condition on the current state and action. So you can read it as we start from the current state and action, and we take a transition to the next step, and then we evaluate the value on the next states. Okay. So this is the notion we're going to use. Okay.
Can you explain this notation again? This PHV?
Oh, it's essentially you can think we start from the current state and action, and we take a transition to the next states, and we take an average over value on the next states. This is like essentially the definition. Let's start from the current state action, and we go to the next states. We go to the next states and take a expectation on the value there. Yeah. So that I think this notation thing is we don't need to write the dummy variable S prime to make it more succinct. Okay. So after we did all the cleanup work, and now let's get to the interesting part. So the first part is about policy evaluation. So policy evaluation asks this kind of question. That is, I think the first step, just remember the goal of reinforcement learning is we want to find a policy so that to maximize the value. So the policy evaluation is essentially the first step. It basically asks a question that given the environment P, that is transition, R is a reward, and more importantly, the policy pi. This is fixed policy. How to compute V1 pi S1, essentially the value we care about. Okay, so the value of the policy pi from the initial states. This, by its name, is like policy evaluation. I want to evaluate how good this policy pi is. Okay, and the evaluation criterion is by looking at the value. So in order to talk about this, we first just recall all the definition that we wrote in the last lecture. Because now we can just purely focus on the Markov policy, so everything here is about Markov policy. And we know the value of Markov policy can be written as the expectation over all the summation of all the future reward. up to h, and RH prime, SH prime, AH prime, conditional SH equal to S, and the QH pi QHSA is equal to expectation over pi summation from H prime over H and RH prime, SH prime, AH prime. The only difference is the condition on the current state is equal to S and action is equal to A. So the question is, again, how are we going to compute this initial value? So there's one naive idea, like a naive approach to compute this, this value at initial state is basically just by expanding the entire probability. By definition of expectation, we can say, because this is expectation over the entire history, entire trajectory, so we can summation over all the possible trajectories and the probability of those trajectories. So one naive approach is we say we can do V1 pi S1 is equal to summation of all the possible trajectory tau h, where this possible trajectory is like S1, A1, till SH, AH. And then we're going to say we compute the probability of generating this trajectory, condition on S1. And then we do the summation of cumulative reward, H equal to 1 to H, RH, SH, AH. Okay. This is essentially the reward of tau h, total reward of tau h. So we essentially just say the probability of generating this tau h times the reward of tau h. This is the definition of the value. However, we we immediately spot this approach of computation is very expensive. It's not very feasible. The reason is this tau h has essentially SA to the power of h entries. So we need to take a summation over this exponentially large number of entries. This is exponential in h. Okay, which in general is really bad if we just want to handle some reasonably long sequence, and this is already extremely large and probably cannot fit in the computer memory. So is there any better way we can handle compute this to evaluate this value? So the secret is again lies in the Markov structure. And we studied the Markov MDP for a reason, just because it's Markov, so a lot of things can be simplified and it can be more feasible. So the way we're going to introduce essentially the key idea is by using dynamic programming. So we will elaborate more later. So first we'll introduce the so-called Bellman equation, which is the most important, one of the most important concepts in reinforcement learning. So instead of just computing this value by brute force, we look at some intermediate relation between this intermediate, the value in the middle steps, VH and QH. So it turns out you can derive Bellman equation by directly expanding this definition, and by this definition you can already see this Q pi, the relation between Q pi and V pi. V pi is probably just taking average of Q pi SA and taking an inner product with of the policy of taking some action A conditional S. Essentially, Bellman equation is exact relation that kind of like establishes the connection between the Q pi and the V pi at the different steps. Okay. So I will just directly write out the results, but you can check both equation is true, like based on this definition. So Bellman equation says VH pi S is equal to summation over A QH pi SA. Okay, so the Q value of if starting SA, and then times the probability of taking action A given S if polar policy pi. Okay. This is relatively straightforward. If you can look at the definition, this will take an expectation over AH. Well, this will not take an expectation over H because A is already specified. And then expectation over OH, like by expanding out, is like exactly like this. And then the next equation is QH pi SA is equal to RH. So the value, if starting from some state action pair at H step, is equal to the immediate value I'm going to receive at this state action pair, and plus the future value. And the future value is equal to the expectation, taking expectation over the next states, that is a sample from this transition probability, and VH plus 1 pi S prime. Okay, and just remember we will use simplified notation later as this pH, VH plus 1 pi SA, and to mean this. Okay. So again, as I promised, this is directly by like a definition of this QH and PH, and you can check offline this is true by just expanding the probability. Yes?
Which is that multiplication supposed to represent like a matrix vector kind of multiplication? Or
what? This one?
Like,
yeah, you can think it's a matrix vector multiplication. Like this V, as I said, is a vector, and you can think this is like transition as a matrix, which is like SA by S dimension. Okay. So why Bellman equation is kind of important? It essentially it's a relation between different values, but it also gives a recursive formula of value at different steps. And I think the important part is this actually kind of already directly gives us a dynamic programming way of compute the value, doing the policy evaluation. Okay. So we just do essentially we will just compute V1 pi S1 by dynamic programming. So let's just write out how we're going to compute this now, given this Bellman equation. So what we can do is we can initialize VH plus 1 pi S equal to 0 for all S. So you can think this is some imaginary stuff because we already stop at H step. So we really don't have anything like at H plus 1 step. So why not just set the value equal to 0 because there's no reward at H plus 1 step and later. So we can just make this as an initial condition. And then we can do dynamical programming for h, little h, equal to h minus 1, till 1. You can compute q pi sa h, that is equal to RH SA. Essentially, we just use the Bellman equation. I've just copied it here, so for clarity. Plus 1 pi SA. This is for any SA. Okay. And VH pi S is equal to summation of A in action set QH pi SA times pi h of A given S. This is for any S. Okay? So this way we can imagine we start from the VH plus 1, capital H plus 1, and then we use this equation to compute a Q capital H, and then use this equation to compute a V capital H, and then Q capital H minus 1, V capital H minus 1, and eventually we get a V1. So if we illustrate this in a figure, that is, we start with some VH plus 1, which is SH, which is S-dimensional thing. Okay, VH plus 1. If we look at this as a vector, VH plus 1 pi is S-dimensional thing, and then use the first equation, we will get to the QH pi, which is S by A dimensional thing. Okay, so we will just use some computation here. And then we will use this QH to get to the VH pi, which is the S-dimensional thing. And then we just use dynamical programming, go onwards, and essentially go back to the V1. Which is also S-dimensional thing. I will just write one more here. QH minus 1 pi, and it's S by A. We have a lot of connections. So it's very easy to verify. By using this dynamical programming approach, we no longer suffer this exponential complexity in computing V1. So now it's so this dynamical programming gives polynomial complexity. To compute V1. And this is a polynomial in H. Essentially, we can think it will make longer, and the entire computation just grows linear with respect to H. Okay, any question up to now? So the question is also, the answer is very straightforward. So to ask how to evaluate the policy, evaluate the value given a fixed policy pi, all we need to do is just do dynamical programming and using the Bellman equation. Okay. So if no problem, we have already talked about the policy evaluation. Then the next thing is, of course, we're not just happy about evaluating a single policy, and our ultimate goal is we want to find the optimal policy. So the question is, how are we going to find this argmax? V1 pi of S1. Okay, this is defined as the optimal policy. So one straightforward idea we can probably think of is, okay, we already have this Bellman equation to evaluate some fixed policy pi. Can we have some Bellman equation type of thing to do the optimal policy? Okay. So one naive idea is we think this entire Bellman equation, if we look at the second equation, it actually does not really depend on pi. Okay, it can be anything because the pi is only appears in the value. Like in terms of computation, there's nothing related to pi. So pi only appear in the first equation, where this is taking average over the probability that indicated by pi. So if we want to do the optimal policy, why not we just focus on all the probability on the action that generate the highest Q value instead of doing some average. So what about every time I just doing the max over A instead of doing some average over A? This is what we talk about. This is what we call a Bellman optimality equation. Okay, so it's again a set of equations, which the only difference is we're gonna change this average to the maximum. So the first equation is V star S is equal to max over A QH star SA. And the second is exactly the same. Q star SA is equal to RH SA plus PV star SA. Okay, so this is our guess, in terms of optimal policy, probably would satisfy something like this. But this is essentially just a set of equations, and how we're gonna get a policy here. So we can read from there, the policy essentially is identified by this taking average, according to the probability that is sampled from pi. So this equation kind of naturally gives a policy that is essentially taking the max over this Q star. So we just define this policy, pi star. H A given S. This is my policy. I get my guess to be the optimal policy, which is equal to the indicator of A equal to argmax A of Q star SA. Okay. Essentially, I'm just going to put all my probability into the action which maximize the Q star. And if there are some tie, I just do some arbitrary tie breaking. I can just focus on one particular action that achieves the maximum. Okay, so nothing very difficult. But as I said, everything is my guess. I think I just modify the Bellman equation, and I kind of my guess, my policy is like this. So the first thing I notice is we kind of first define this V star. I don't even know whether this value is corresponding to any policy, it's a value for any policy. I don't know. But we can first argue that V star H is actually just equal to VH pi star. And QH star is equal to QH pi star. Okay. It's easy to prove this because the Bellman equation, because pi star is some particular policy, and so pi stars, you can think the value of pi star satisfies the Bellman equation. And if you write out the Bellman equation of pi star, you can realize this is exactly equal to the Bellman optimality equation. Like they looks exactly the same. So the first thing is we convince ourselves when we write out this Bellman optimality equation, this actually corresponds to the value of this particular policy. Okay, this is not some arbitrary thing. It's kind of like corresponding to some particular policy. Okay, and the second thing we're gonna claim, proposition 2. Is I'm gonna claim this is not my wild guess. Actually, this is in particular indeed the optimal policy. So we will say pi star is the optimal policy. I think we kind of because we're doing like theoretical work, theoretical like establish foundation, so we want to like make sure the logic is like is clear. Like we don't have like some cyclic reasoning in the middle, but like in the end, after you kind of knows everything, you just know this is like Bellman optimal equation. This is like equal to the Bellman equation of pi star, and everything is like pretty straightforward. Okay. Okay. So now we will prove this claim. So in order to prove this claim, we actually will prove an even stronger claim, and where this claim is like a special case of my stronger claim. So we will actually prove that V pi star H of S. This is like the value of pi star at step H to state S. Is actually equal to max of all the Markov policy, pi in Markov policy, VH pi S for any H and S. Okay, I just want to explain a little bit difference between those two claims. I think the original optimal policy only says you need to, this is only defined you need to maximize the initial value, initial value at initial states. Well, this essentially says pi star is the optimal policy for all states and all H steps simultaneously. Okay. So that means like if you look at different states, the optimal policy is actually not different policy. They are actually exactly the same policy, which is the pi star we define here. Okay, this is a much stronger claim. But you can think of one very special case is I just pick H equal to 1, S equal to the initial states, and this gives what I want to claim in the proposition 2. Okay, so again, we will do induction. So the only difference of this induction is we no longer do induction from the first step to the last step, and we will do the opposite direction because this is optimal policy. So we will first argue the last step is optimal, then the second and last step is optimal, and then going backwards. Okay. So the essentially logic we're going to do is we're going to argue this VHS equal to max pi v pi h s. This is what we want to say in here, and we will argue this by we first say first step q pi star sa is actually equal to the max pi q pi h sa. And the second step is we will use the next step to argue this. That is VH plus 1 pi star S is equal to max pi VH pi S. Okay. This is for any S, for any SA H A. This is also for any S. Okay, so we induction backwards. We will argue if the value at h plus 1 step is already the optimal one, then going backwards at h step, q value is optimal, then v value is also optimal. Okay, let's always start from the base case. Base case is the final step, and I think we said we can use the dummy step, which is h plus 1 step. In the h plus 1 step, there is no reward going forward. So we can immediately say this is true. Because there are really no policy in the future, and everything is just equal to 0. So we'll quickly do 1 and 2. Sure. Let's do this one first. First, we look at the max pi, QH pi, SA. And by Bellman equation, we know this is equal to RSA. And because R does not involve pi, so we no longer need to take a max over this pi, and we can push max inside. We say this is a max pi over expectation S prime sample from P, SA, and VH plus 1 pi S prime. I think the important thing is now we want to switch the order of the max and expectation. So in general, let's just be more concrete. We want to essentially do max pi summation over S prime, P S prime given SA, H and VH prime plus 1 pi S prime. And in general, we cannot swap this max and expectation, max and summation. So in general, if we have this max fx plus gx, like we had 2x thing, and we want to take the max. In general, this will be smaller than the max of fx and g plus max of gx. Okay, just because this max can be achieved at different places. If this max is achieved at different place, then this is strictly less than that. However, if we have that argmax of fx is equal to argmax of gx, that is, their max can be achieved simultaneously, then we actually have this equation that is max x of fx plus gx is precisely equal to max x and max gx. And this is essentially what we can do here, because by induction hypothesis, we can say the pi star actually achieve the maximum policy simultaneously for all the state S, for all the next state S. That is, the maximizing policy here for pi is always pi star, no matter what S prime is. So we can say this is actually equal to, we push the maximization inside. Because all the maxes are achieved simultaneously at pi star, so this is just equal to VH plus 1 pi star S prime. Okay, this is because and finally, we realize this is just a Bellman equation for pi star, and this is equal to QH pi star SA. Okay, I will just do like 2 more minutes to finish the proof. I think similarly, we can also just argue the same thing. That is, we start from the max h, VH pi s. This, again, by Bellman equation, is equal to max pi summation a, QH pi SA of pi a given s. And this is h. Okay. So the important part is we can realize we can like separate this pi, because this pi is essentially a collection of all the possible future policies. So we have this, we can take a max over pi h here and a max over all the future policies, summation a, QH pi SA, and pi h a given s. And the other thing is realize this Q value actually only depends on the policy in the future. So it doesn't depend on the current policy of current step, because current step we're already taking some action A. So this only depends on pi h plus 1 to pi capital H. And again, we can use the same argument to that because we achieve the max at the same place, so we can essentially swap this max inside, and which more or less give what we want. And it's just equal to max over pi h summation A, because we can push the maximization over all the future policy inside, and it becomes a Q star SA and pi h A given S. And finally, we know the maximization of the policy achieved at, we put probability 1 onto the maximizing action. So this is just equal to the max over A, Q star, SA, Q pi star. And which is equal to VH pi star S. Okay. I think this finished the proof that we argued this pi star is an optimal policy. In the next lecture, we'll continue talking about some planning algorithm, essentially. What is the algorithm we're going to compute the optimal policy? And then we're going to start talk about a little bit more challenging setting where the environment is unknown and we need to, how we're going to develop some tools to use data to estimate this environment to learn the MDP. Okay, thanks.